All right, welcome to The Explainer. Today, we're diving into the science of tiny, tiny patterns. We're talking about a technology that's so small you can't even see it, but it's so powerful, it literally shapes the world around us.
Okay, let's kick things off with a question about something I'm willing to bet you use every single day, your phone. Have you ever stopped to wonder how they actually make those impossibly small, perfect little lenses inside the camera?
Well, believe it or not, the answer is surprisingly simple, at least in concept. It's kind of like a super high-tech version of a waffle iron. Seriously, you're basically just pressing a really detailed pattern into a material. The big difference? This is all happening on a mind-bogglingly microscopic scale.
But, just like with any good recipe, it all comes down to having the perfect ingredient. And in this case, we're not talking about waffle batter. We're talking about a very special kind of plastic that makes this whole thing possible.
All right, let's get into it. Tiny patterns, but a huge impact. We're going to see exactly why this kind of microscopic manufacturing is basically a cornerstone of all the tech we can't live without.
So let's meet the Wonder Plastic, the hero of our story today. The star of this whole show is a specific kind of polymer. It's a material scientists picked for some really unique and super useful properties. And its name is PMMA.
Yeah, that's a mouthful. Its full name is polymethyl methacrylate, which is exactly why we all just call it PMMA. Now, the most important thing to know about it is that it's a thermoplastic, and that's really just a sciencey way of saying you can heat it up, it gets all soft and moldable, and then when it cools down, it gets solid again. See? Perfect for pressing a shape into.
And I guarantee you've seen this stuff a million times. You probably just know it as plexiglass or acrylic. Yep, that super clear, tough plastic they use for everything from airplane windows to giant fish tanks. That's our high-tech hero. So why this plastic? What makes PMMA so special? Well, it's got a whole set of superpowers. For one, it has excellent optical properties. It's super clear, which is perfect for things like lenses. It's also a thermoplastic, which we just learned means it's amazing for making high-fidelity replicas. And on top of all that, it even plays nicely with other polymers like PC and PET. It's the total package. Okay, so now we know the what, let's get to the how. Let's talk about that micro waffle iron. This elegant process is called polymer embossing, and we're about to see exactly how it works.
And honestly, it boils down to a pretty simple four-step dance. Step 1, you heat up a film or a disc of PMMA until it gets nice and pliable. Step 2, you press a microscopic mold, think of it like a tiny intricate stamp, right into that soft plastic. Step 3, you cool it all down while keeping that pressure on. That's what locks the pattern into place. And finally, step 4, you release the mold and voila! You've got a perfect replica left behind in the PMMA.
Now, even though the idea is simple, the science behind it gets really cool. Take that first step, the heating part. There are a couple of ways to do it. You've got your traditional hot embossing, which, just like it sounds, heats the entire polymer up nice and evenly. But then you have ultrasonic embossing, which is way faster. It uses these super high-frequency vibrations to create a bunch of localized heat, like instantly. It's a much more targeted way of doing things.
Okay, but here's where things get really interesting. Let's talk about the science of the squish. Because making sure every single microscopic copy is absolutely perfect, that's a huge challenge. It's not just about squishing plastic, it's about incredible precision. I mean, just think about it for a second. We're talking about a process where everything is measured in micrometers. That's millionths of a meter. There's literally zero room for error. The tiniest little imperfection can completely ruin the final product. So how do you get a flawless copy? Not just once, but millions and millions of times. Now that is a serious scientific challenge.
To solve that problem, scientists have to be total experts in what's called the material's thermomechanical behavior. And all that really means is they have to understand exactly how the plastic deforms and responds to forces, stress and strain, all that good stuff, when the temperature is changing.
And that means they're juggling a whole bunch of different variables that they have to get just right. We're talking about way more than just the molding temperature and the pressure. They have to control the strain and the strain rate. They have to account for things like work hardening, where the material gets tougher, or even strain softening, where it gets weaker. They even have to predict the internal elastic recovery. That's how much the plastic tries to spring back to its original shape. It is an incredibly complex physics dance.
In temperature, temperature is one of the biggest ones. There is absolutely a Goldilocks zone here. If it's too cold, you get a poor copy because the pattern doesn't really form. If it's too hot, the plastic gets too runny and the copy comes out all deformed. But when you hit that temperature that is just right, you get a perfect 98% quality copy. Getting this control dialed in is absolutely crucial because this is what prevents those tiny catastrophic defects. Think about a medical diagnostic device. If one of those tiny microchannels gets blocked or deformed because the temperature was off, well, the entire device just doesn't work. The stakes are really high.
Okay, so let's zoom back out for a second. We've seen the plastic, we've seen the process, we've seen the science of the squish. Now let's see how it all comes together to shape the miniature world that's all around us and inside our tech.
So where do we see this stuff in the real world? Everywhere. This one process is the key to making tons of tiny components. We're talking about the micro lens arrays in your camera, the micro channels in those lab-on-a-chip medical devices, the light diffuser films that make our screens brighter and more efficient, even creating functional surfaces with custom properties like making something super waterproof. It all comes back to this amazing stamping process.
So, what are the big takeaways here? What should you remember from all this? 3 things. First, a really common plastic, PMMA, or acrylic, is actually a secret hero of high-tech manufacturing. Second, this process called embossing is basically a super precise stamping method for making microscopic patterns. And third, and maybe most importantly, mastering that science of squishing is the key that unlocks all the miniature technology we rely on. So in the end, when you realize we figured out how to stamp almost any microscopic pattern we can dream up onto a simple piece of plastic, well, that just opens up a whole universe of possibilities. It really makes you wonder, doesn't it? What future are we going to build, one tiny, microscopic pattern at a time?